We are given an overall reaction, which is nitrogen dioxide plus carbon monoxide yields carbon dioxide plus nitrous oxide. I'm going to call that NO because I actually don't remember what that's called. So we're also given two mechanisms. We're given two mechanisms that I propose that will both equal this overall reaction. The first mechanism that we're given is NO2 plus CO yields CO2 plus NO. For the rate law for this one, we can take it straight from this equation because it's the reaction is just proposed to be one step. If it's multiple steps, we have to look at some different things. But since this is just one step reaction that's proposed, we can just take the rate straight from it, from the coefficients. So the rate equals K constant times the concentration of NO2 to the first order, because there's no coefficient here, and carbon monoxide to the first order as well, because there's no coefficient there. Then it's also proposed a mechanism 2, which is a two-step reaction, where in this slow step, like, what do they call it, the slow equilibrium step. This is the rate determining step though, that's the most important thing we need to know. And then there's also a fast step to it also. In the slow step we have NO2 plus NO2 yields NO plus NO3. And in the fast step we have NO3 plus CO yields NO2 plus CO2. So to determine the rate law for this mechanism, we would have to take it from the slow step. I feel like I'm missing a word there, but yeah. We're taking it from the slow step because it's the rate determining step. So we would do the same thing that we did up here, which is rate equals the K constant times NO2 to the first order times NO2 to the first order, because there are two NO2s, neither of them have a coefficient. If you did put in the reactant CO, it would be to the 0th order because it doesn't count in the overall reaction, which is what we're really looking at overall. You can rewrite this as rate equals the K constant times the concentration of NO2 to the 2nd order, since there are two of these, and this doesn't count towards it. So those are the rate laws for each mechanism, and then we're asked to design a kinetics experiment to distinguish between these two proposed mechanisms. To distinguish between these two proposed mechanisms, we can look at what the nitrogen dioxide is to the order of. We can compare NO2 to the first order to NO2 to the 2nd order. So if you just looked at the rate order for nitrogen dioxide, you would have that for the first mechanism, it's proposed to be nitrogen dioxide to the first order, and for the second mechanism, you would have that the rate is equal to the K constant times NO2 to the 2nd order. So to compare these to look at, if you collected data and it ended up being mechanism 1, you'd have to isolate the nitrogen dioxide and see how it changes over time. And to look at that, you'd have to keep the concentration of carbon monoxide the same so that you could see how the nitrogen dioxide changes. So we would have a few different experiments where you would keep the initial concentration of carbon monoxide the same each time. And then you would see as the initial concentration of nitrogen dioxide doubles, we see from 1 to 2 it doubles. And we'd see how the rate also changes, which if it was mechanism 1, which is what's proposed up here, then we would see that also doubles. And we know the rate equals the K constant times the concentration of NO to some exponent, and we're ignoring the CO because we're just gonna compare the nitrogen, I probably put a 2 here, the nitrogen dioxides. So we have that the concentration of nitrogen dioxide raised to some exponent equals the rate, which is here. So we have this doubled and this also doubled, so we have 2 to some exponent equals 2. Well, we know that 2 to the first power is 2. So that would mean that nitrogen dioxide is to the first order, which would mean that if we graphed this, we would get a linear line with an R-squared value of 1 if we took the natural log of the concentrations times the time, which would be, experiment 1, 2, 3, 4. And that would tell us that nitrogen dioxide is first order, which is what was proposed here. So if that was true, then that's what the graph would look like, and that's what the data would look like. You'd have the concentration of NO2 doubling and the rate also doubling, so that would just be the first order. For mechanism 2, we can do that same thing. Just looking at the nitrogen dioxide, we'd have that the rate equals K times nitrogen dioxide concentration to the second order. So if that's true, then we could run that same experiment where the initial concentration of carbon monoxide is the same each trial, but the initial concentration of nitrogen dioxide changes each trial. If you double it each time, and you see that the rate quadruples, then we do the same thing that we did over here. We know that the rate equals the K constant times the concentration of NO2 to some exponent. So if this doubles, we have 2 to some exponent equals 4 since the rate quadrupled. And we know that 2 squared equals 4. So that would mean that nitrogen dioxide is to the second order. So if we graphed that data, we would get a straight line when 1 over the concentration of NO2 is plotted versus time. We get an R-squared value of 1, which means that it's a straight line. And we would know that NO2 would be to the second order. Did I forget anything? We got the rate law, and make sure you explain your results of the experiment would be if each mechanism was correct. So overall, if mechanism 1 was correct, you would see that the data was plotted with an R-squared value of 1 when the natural log of the concentration versus time was plotted. But if mechanism 2 data was correct, then you would see that the 1 over concentration of NO2 versus time, which is the experiments or the trials, would be a straight line R-squared value of 1 when these are plotted versus each other.